compiled to efficient and readable C code by Clément, Chavanon, and others, mainly from Inria, IRISA, blah, 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 and from KTH. It's like four affiliations. Over to you, Clément.
Thank you for the introduction. Is the mic working? Yeah, okay, thanks. So here, hello everyone, I'm Clément, and I'm going to present work on a domain-specific language. Yeah, domain-specific language that is aims at facilitating the verification of system code, and that is compiled to both efficient and readable C programs. So this is a joint work between Inria and KTH. So the motivation behind this work is that verifying system code is challenging because those programs are written in low-level languages such as C, for example. So you have to reason with pointer-based semantics, and you have to maintain complex memory invariants when you reason about those programs. So what we usually do when we want to verify system code is to work with higher level abstractions. For example, using a refinement approach in which we are going to define several models of the system at different abstraction levels. And we are going to do refinement proofs within those models, which means that for a given model, we are going to prove that it is a valid implementation of the higher level abstract model. And we have wonderful tools to do that mechanically nowadays, which are proof assistants, that are tools to that have a programming and a specification language that are used to reason about programs. However, when we use this approach, there is a semantic gap between the very high-level abstract model and the source code that we would like to run on the hardware. So in this work, we took the approach of a compilation to automatically derive source code from abstract model. And the ultimate goal is to have a verified compiler. So this means that we want to check that the compiler does not introduce bugs when it compiles to source code. And more specifically, in our cases, we want to start from ROC programs. So ROC is one of those proof assistants. And we want to generate C code, but not any type of C code. C programs that are suitable for embedded systems means that fit the constraints of those systems, memory-wise and time-wise. So ROC, the semantic gap between ROC and C is that ROC is a very high-level programming language, purely functional. So it means that there is only constant values, and it has to be executed under runtime, so it's not suitable for embedded systems. So that's why we come with our own domain-specific language, which is called Baroque, which is still purely functional but very minimal. And it can be seen as a ROC subset with a particular programming discipline that I will talk about in a few slides. So to achieve a certain efficiency, we compile with in-place updates. So basically, we did not do copy when we compile to the C code, but values in the C programs are mutable, and so that's what we call in-place updates. We also made a very pragmatic choice to compile to readable C code, because our goal is to bring those tools to the system programmers community. So we think that it's important to generate C code that can be reviewed or easily debugged by system programmers. Finally, because system code requires fine-grained control over the memory layouts, we have some annotation in the language that allow to control these layouts. And as a proof of concept, we implemented the S3K separation channel, which was originally created at KTH. So there is already successful stories in the literature that are using compilation to implement system codes, for example, Lostar for cryptographic algorithms and Cogent for file systems. And what we wanted to do with Baroque is to kind of having a compromise between those two works, so have a lightweight approach so that the language is minimal and easy to learn, and having the possibility to generate idiomatic C and readable C code for the reasons I mentioned in the previous slides. And also we needed some features such as arrays, and more specifically arrays of non-primitive values that were not supported by Cogent, for example. So the rest of this talk is divided in two main parts. The main part will talk about the Baroque language and its compiler, and the second part will talk about the Baroque part of this microkernel called S3K. So I will not talk about proof in this talk. So to give an overview about the compilation architecture of Baroque, the first step is to compile the functional language Baroque into an imperative one called imp1. So the compilation process is divided into multiple phases to ease the proof of correctness of this compilation. And the first three passes are inspired by a work of Bowman published at Uppsala 2 years ago. Because compiling functional programs with in-place updates is incorrect for the majority of functional programs, we have to check that for a given program it's actually correct. So we have this static analysis that is performed on imp1 that does this check. And we finally introduce another intermediate representation on which we perform some optimizations to make the code more readable and idiomatic. So those optimizations are copy propagation and globalization. So globalization is the fact of replacing some function parameters by global mutable variables. And sorry, finally, we generate C. There is one slide missing here, sorry. So that's very, oh. Yeah, sorry, there is a bug in the slide. So I'm going to talk about a little more of the language with an example. So this is the implementation in Baroque of buffers. So we have a record type buffer with, which define the length of buffers and the content. So the brackets here are used for declaring an array of 64 unsigned integers. And then we define the buffer write function that writes a value v into the buffer b. So basically this function first checks that the buffer is full. If it's the case, it does nothing and just returns the buffer. And if the buffer is not full, it writes the value v at index length of the buffer content. So to give you an idea of how the static analysis works, I would like to run a concrete execution of this program with the following inputs in the two semantics. So in the copy semantics, in which we only do copy, and in the in-place semantics, in which we do in-place updates, which is the semantics that the compiled C code have. So in the copy semantics, the buffer B is associated with buffer value. So just a functional value, but in the in-place semantics, we introduce a memory. So the buffer B is a pointer to a buffer record, and the buffer content is a pointer to an array of unsigned integers. So when we execute the first expression, so we read the contents, b.contents, and put this in a variable ct. So in the copy semantics, we do a copy of the buffer content. But in the in-place semantics, what we do is that we have a pointer that is an alias to the buffer, the input buffer content. And when we do an update in the copy semantics, again, we copy the content of CT and put it into CT1, and we update the value at index 2, and we put the value 7. But in the in-place semantics, what we do is that we directly mutate the memory. So we replace 0 here by 7. And CT1 is also a pointer and is an alias to CT and points to the buffer content. I can continue to execute this program. And at the end, we obtain those two final states. So in the copy semantics, there are all of these local variables that were copied from each other. But in the in-place semantics, B1 and BRES are aliases to the input buffer. And as I said previously, CT and CT1 are aliases to the input buffer content. So if we look closely at the two states, we can see that some memory access path evaluates this, differently in the two semantics. So for example, b.flanks evaluates to 0 in the copy semantics, but it evaluates to 3 in the in-place semantics because we did in-place updates. So the static analysis tried to compute those invalid paths. And then it checks that in the return value, so here it's the return buffer bres, everything is coherent in the two semantics. So in this example, this is the case. So the length and the content of the buffer are the same in the copy and in the in-place semantics. So we say that in the in-place semantics, the program behaves the same as in the copy semantics, and we accept the program. However, let's say that we made a mistake when programming this function, and instead of b1.length, we wrote b.length. So in this case, it means that the result buffer here will not contain the updated content because it was contained in b1. So if we execute this new version of buffer write, we obtain this final state. And what we can see here is that in the copy semantics, the value has not been updated here, but in the in-place semantics, because we do in-place updates, it has been updated. So this memory path that has as origin bres does not evaluate the same in the two semantics, and we reject this program. So to summarize how the static analysis works, basically for a given function, and assuming that all of the arguments are valid, the static analysis will compute this set of invalid paths that catches the incoherence between the two semantics, and then it checks that the return value is associated with any of invalid path. If it is not the case, then we can accept the program. So we can informally replace what the static analysis enforces with this following programming discipline, which is always use the most up-to-date memory path to access a value. Okay, so now let's see how this program is compiled to C. So I put again the definition of buffers in Baroque. And the associated C type is the following. So Baroque records are compiled to C buffers and C strict, sorry. And the contents of the buffer becomes a pointer to an array of unsigned 64-bit integers. And as in the example before, the memory layout of this unallocated buffer is the following one, with content being a pointer to an array. If we do not want, if we want to remove this indirection here, we can use what we call an unboxing operator, which is the sharp operator here, which say, okay, let's remove this pointer and flatten the buffer content inside the buffer record. And as we also need to specify the length of the array so that it can be compiled to C. And the memory layout of this new type is the following. So everything is just flattened, and we do not have indirections anymore. OK, so now let's see how we compile the buffer write function. I highlight here the lines that correspond in the Baroque codes and in the C code. So what we can see is that some assignments and some local variables are not present in the C code. This is an optimization that we do on the IM2 intermediate representation. So because in the in-place semantics, creating and reading, modifying and reading the memory creates aliases, it happens that B1 and BRES and CT1 are useless variables. They become dead variables, so we are able to remove them, and this is the result that we obtain after this optimization pass. So we directly mutate here the first variable CT and the length of the input buffer B. And also concerning the function signature, there is a one-to-one mapping between the Baroque signature and the C signature. So the input buffer is a pointer in C, and the return value is also a pointer, which corresponds to that on Baroque code. And now I'm going to talk more details about S3K, which is a simple secure separation kernel. So it's a kernel developed at KTH. It targets RISC-V embedded systems, and it's based on capabilities. So originally, the implementation is in C and assembly. And the goal of this kernel is to guarantee some security properties which are related to spatial protection and temporal protection. So the goal of spatial protection is to isolate each processes from each other, and it enforces thanks to the PMP RISC-V mechanism. And the temporal protection relies on first the temporal reference to flush the cache at its context switch, and it allows to protect against side channels. And they also add time padding to avoid the execution time of processes to interfere with the execution time of other processes. And a little bit more about capabilities. So capabilities are tokens and enforceable tokens that grant access to a system resource. And one of the core logic of S3K is to manage dynamically those capabilities. So the main two operations are capability derivation. So a capability is going to delegate its rights to children capability. And the reverse operation, which is capability revocation. So the capability will reclaim the rights that it previously allocated to children. So the original implementation of Baroque was about 2,000 lines of C code and 200 lines of assembly. The number of lines for the Baroque implementation of S3K is roughly the same, so 2,000 lines of Baroque, but we have remaining C code in this implementation. And this C code is mainly used for interaction with the hardware and also some loops that could not be ported to Baroque for the moment. And thanks to this unboxing operator that changes the memory layout, we achieved the same layout for the kernel tables. To test that the kernel, the Baroque implementation of S3K was reasonably efficient, we run some benchmarks on real hardware, so on FPGA. And in this benchmark, we have two processes, a client and a server that are talking to each other. And we measured the time that the kernel take to handle the message sent by the client and the time that it took to handle the reply sent by the server. So in this setting, we have approximately 3% overhead introduced by the Baroque code for the runtime trip, which is the sum of those two times. We also rerun those benchmarks by adding a temporal fence just before sending the message for the client and the reply for the server. So basically, the temporal fence flushes the cache. And in these settings, the overhead is higher and is about 8% for the runtime chip. OK, so let's now conclude. So what we did in this work is that we have a new domain-specific language that is embedded in ROC and that we compiled to C. Something that I didn't talk in this presentation, but if you're interested, you can read the paper, is that we define a semantics for Baroque, and we prove that this semantics is sound with respect to how the ROC interpreters interpret the Baroque programs. We have a compiler that generates human readable and reasonably efficient C code. And finally, we have an implementation of a state-of-the-art separation kernel. And for the future works, we would like to dig into some proofs, so proof of the compiler on S3K, and adding some more features to the language and finding more case studies for Baroque. Thank you for the attention. I will take some questions.
Thank you. Are there any questions?
Thank you. Andreas Koch, TU Darmstadt. I have a very minor question on this, but we are struggling with the same topic in my group currently. So I'm wondering, why did you compile using just -02 instead of 03?
It was an advice of one of the co-authors that say it's safer to compile with 02. So. Yeah.
But it's a performance difference. 03 will run faster, quite a lot faster in some cases.
Yeah, sure. But so I'm not the compiler C expert, and so we reused how the previous benchmark on S3K was done, and it was compiled with 02. Yeah, I think the main reason why it was not. That's an advantage to compile with 03, from what I understand. But yeah.
Okay, thank you.
Thanks. So you position this for microkernels, right?
Yeah.
But you have to also deal with assembly. So why is it not possible to translate your Baroque directly into assembly if you have the specification of assembly?
So what you will do is to define abstract function in Baroque, so a function that do not have an implementation in Baroque and that serves as the interface for the assembly implementation of those functions. And does that answer your question?
So let me.
Yeah.
The answer is that we already have a verified compiler from C to assembly.
Yeah.
Oh, okay, that was.
Okay. Okay. So for everything can be written in Baroque, including the all the stuff relevant to assemblies, if I get it right. Yeah.
I mean, the thing that our assembly codes remain assembly codes.
Yeah.
It cannot be written in Baroque.
So if I want to write a context switch,
yeah,
for example,
so
then I need to write some assembly, right?
Yeah.
That's what we do nowadays. But so can we also do some stuff in Baroque for context switch?
No. So for example, context switch typically will be written in assembly. Yeah.
I think my question was answered already. I wanted to ask about what is the subset that you compile to, and if that is the subset corresponding to ComCert. But I think that's, you're using ComCert then.
Yes.
All right.
So the subset of work, right, or the subset of C, yeah. So we are targeting C syntax, the source language of ComCert, and I mean the subset is using the records, I mean structures, enumerations, ifs and else switch statements, and pointers, and yeah. Approximately.
So I had one last quick question. Yeah. The style in which you have to write your functional code has to look pretty much very idiomatically like C. It's this continuation of let. Yeah. What if you wrote it differently? Would you get very bad behavior? Inefficient behavior.
So what you will have is just not a one-to-one mapping between the Baroque and the C code, but it does not affect the performances of the code.
Okay.
Yeah.
Great. Our next talk is on a pointer ownership model. Yeah, let's give a round of applause. Sorry. Yeah. Thank you.